Hi, everyone. My name is Chen. I'm an assistant professor at Texas A&M University. So I want to start my talk with this example of hallucination in large language models. So actually, I tried this a few days ago. It seems Gemini still has this problem. So hallucination is a very common issue in large language models, and what we also need to realize is that hallucination is not exclusively existing in large language model. It also exists in other AI models, like those being used for generative design for materials. So I'm going to demonstrate using this example. So this example we have, this is an inverse design problem where we are interested in designing this so-called nacre-inspired material where there are two phases. It's a two-phase component. You have the rigid material being here. Those tablets are those rigid materials, and those they are soft materials at the interface of those tablets. So it has a good property of, for example, high toughness. So we are interested in design the stress-strain relation of this material, basically the nonlinear mechanical behavior of this material by controlling the interface material property, so the property of those soft materials. So this is an inverse design problem, and for inverse design problem, there are a lot of work on it. So using the conditional generative model to solve this problem. And it's a reasonable choice to use a conditional generative model because in inverse design, a lot of times you got multiple feasible solutions for even just one target. So what the conditional generative model can do is that it can learn a distribution of the solution given the target. So basically, you can sample from this distribution to generate multiple solutions, multiple potentially feasible solutions, and solve this non-uniqueness problem. And you can see in the metamaterial design community, there are already some works that use this deep generative model to diffusion model to be specific to solve this inverse design problem to generate nonlinear mechanical metamaterials. So we want to do the same thing. We want to first generate a bunch of data and train a diffusion model to do this inverse design. So this is a data set we had. So we generated a bunch of designs, and then we use FEM to compute the stress-strain relation. These are the stress-strain curves we saw in the data set. And then we try to use a diffusion model to solve this inverse design problem, right? And we want to do something more challenging. We want to look at those targets. Those two targets, as you can see, it's very different from those from the training data, right? So we got these out of distribution targets. We want to see how the diffusion model perform, and this is what we got, right? So none of those generative solutions actually satisfy the target we set. So what is the problem here? So basically, the problem is obvious. We got out of distribution prediction, right? So the question, one straightforward question to ask is that, can we avoid this out of distribution targets by just simply diversifying our data set? The answer is no, and here's why. So we have this design space, right? So we normally start by generating data, and we can control the distribution of our designs very well. We just can randomly, uniformly sample our design space to generate design data, right? And then the next step is to use FEM or doing experiments to get their responses. And the problem here is that we do not have control of the response space. I mean, the distribution of our data in the response space. So in that case, we train this conditional generative model to map the response to the designs, and hopefully, given a target, we can map this target to the designs. But the question is, if the target is out of distribution, can you really trust the model prediction, right? So the answer is definitely no. So to try to mitigate this problem, we try to propose a new method called GUIDE, which is short for Generative and Uncertainty-Informed Inverse Design. So what we do is as follows. So we use the same data set, right? We don't change the data set, but instead of training a generative model, we try to train a predictive model By the way, this predictive model is also much easier to train than the generative model. So after we train, more importantly, we also allow this predictive model to have uncertainty quantification capability, so that when you have a target, you can basically derive the likelihood of this of any design in the design space satisfying this target. So it's basically compute a probability of target satisfaction. Okay, so then based on this likelihood, we can sample designs from the design space based on this likelihood distribution using MCMC. And then more importantly, we can also use this likelihood to indicate a confidence of our model for any decisions any solutions it generates. So basically, we can then decide whether we can trust our model on this solution or not. So to evaluate this method, we do not just look at the accuracy or the feasibility ratio of our generative designs. We also look at the relationship between the likelihood and the feasibility rate. So suppose if we have a good model, then there should be a high correlation between the likelihood and actual feasibility ratio, because with higher likelihood, we are hoping that the generative designs actually has a high probability of satisfying the target. So we can measure that by looking at the feasibility ratio here, and then we can compute some correlation measure, right? So we can quantify the correlation. So using Pearson's correlation coefficient, for example, and in this case, we can show that we have there's a high correlation between the likelihood being estimated and the actual feasibility rate. So here I'm showing two actual design examples. We are more interested in this out of distribution targets. So on the left, you can see this. Our target is this ultra stiff material design. So the blue curve here is the stiffest material from the data set, and the red line here shows our target. So we are only focused on the stiffness in those cases. So you can see that we can generate feasible designs. On the right, it's another example of ultra soft material generation. So basically, again, the blue is the softest material from data set. The red is the even softer, right? It's our target, which is even softer than softest material in the data set. And then we show that we need to extrapolate from the original training data set to be able to generate those feasible designs. And here we are looking at this is another design case where we look at the entire stress strain curve. And again, red here is our target. Blue here is the best match, basically the closest match from the training data. And we can see on the right, we compare the designs generated by guide with those generated by conditional diffusion model and the genetic algorithm. And interestingly, genetic algorithm didn't find any feasible designs. So here in the right plot, we only show feasible designs, how they distribute in the design space. For conditional diffusion model, we can discover one feasible designs, but for guide, we can discover multiple. We also compare the feasibility, diversity, and novelty of those solutions. And for those of you who are interested, feel free to look at the paper. But here, so I want to come back to the original, the two targets that I mentioned before. So obviously, for conditional diffusion model, it didn't generate any feasible solution. So did the genetic algorithm-based optimization method. And interestingly, for guide, it does not generate any solution because it cannot find non-zero likelihood designs from anywhere in the design space, which we think is good because we think that machine learning models should know their limits. If you are not sure about this target, if you haven't seen something similar, then you probably shouldn't generate anything. Thank you. That's all.
Questions from the audience? Great.
I'm just curious, so the stress strain curve depends on the material model as well. So let's say you have a hyperelastic material, and suppose your target distribution is, I don't know, an elastoplastic material, right?
Yeah.
So I'm just wondering, because would you envision a future where it's also able to pick up the right material model and, and so on and so forth, or maybe, just maybe this is my question is, I know, about, you didn't talk much about the material model, and maybe I just wanted to know more about that.
Yeah, definitely. So the material model, it's basically decide the data set you can get, right? So if you are essentially, so right now what we are doing is that we just define this material model, right? This kind of Naker inspired material, and then we just run FEM based on this single model, and then get those design. Of course, if you can potentially get a larger coverage of the design space and also the response space by kind of considering different types of materials, right? Material model, constituted models. But the problem is you always get some limit. You always have some limit, and this kind of problem will still exist. This out of distribution target problem will still exist, right? So in that case, this is still going to be a problem, right?
Yeah. Maybe one more question. Actually, I have one.
Yeah.
So when you're thinking about out of distribution, I'm wondering, like, what do you see as like the future step? Like, do you imagine maybe the model says, I don't know, and doesn't answer, but then can it go back and say, I need to collect this data, you run this experiment, and then I will know?
Yeah.
Or this type of kind of like iterative process. Is this something that you've thought about?
That's a good question. Yeah. So I think the next step would be doing some exploration based on active learning, right? So basically you can say that, okay, I don't know, I mean, in this design space, I'm very uncertain. Like across the entire design space, I'm not sure which satisfy this target. But if we quantify the uncertainty, then we still know that maybe this is like more likely to satisfy a target than this one. So maybe then we should look at that design, which has a higher likelihood, even though the likelihood is very low. Right? We may need to kind of go towards that direction and then start to explore that, and then make it iterative. I think that's a good idea. Yeah.
Awesome.
Good
Great.
point.
Thank you. Let's thank the speaker.
Yeah.
Front.